Good day everyone, I'm Maria Victoria Migo-Sumagang and I'll be presenting our work entitled Fuzzy Linear Programming Model for Planning Negative Emissions Technologies Portfolios with Synergistic Interactions under Capacity Constraints. This work is authored by myself, Professor Raymond and Professor Kathleen Aviso. We are from the De La Salle University, Philippines. The presentation is divided into 4 parts, and we will begin with a discussion on negative emission technologies. Climate change is considered as one of the greatest challenges that humanity is facing right now. The Paris Agreement in 2015 has set the stage for limiting the global warming well below 2 degrees Celsius and pursuing efforts to further limit it to 1.5 degrees Celsius. The figure from Fuss and colleagues in 2018 shows the pathway in achieving the 2 degrees target versus our business as usual carbon dioxide emissions. It also shows that sometime between today and the 21st century, we have to reach net zero emissions. IPCC models have shown the importance of negative emission technologies, or NETs, in achieving the required negative emissions to reach net zero. And studies have reported that we need to target an annual negative emissions between 2.18 and 6.44 gigaton carbon equivalent per year for 50 years to mitigate climate change. And these negative emission targets can be reached using negative emission technologies, or NETs. The figure from Mix and colleagues in 2018 shows the various negative emission technologies, or NETs, according to capture method. NETs that rely on photosynthesis include afforestation and reforestation, or AR, soil carbon sequestration, or SCS, biochar, or BC, bioenergy with carbon capture and storage, or BECS, and ocean fertilization, or OF. While NETs that rely on chemistry include direct air carbon capture and storage, or DACS, and enhanced weathering, or EW. To reach the scale of negative emissions required to mitigate climate change, the wide-scale implementation of portfolios of NETs is necessary. However, the wide-scale implementation of these technologies will have environmental impacts and may also compete with other societal priorities like land and water for food production. Hence, various literature have studied both the potentials and impacts of these NETs. This table shows the potential negative emission capacities of selected NETs, as well as the environmental footprint of these technologies. As we can see from the table, each technologies have varying capacities, and for each net we are given a range of values. These values consider limitations, say for example, in the available biomass supply for BECS, or suitable soils for storage for biochar, etc. The nets also have varying environmental footprints. Some technologies will require more of one resource compared to the others. In planning the wide-scale implementation of these technologies, it is important to consider this data as constraints for feasibility and sustainability. Another feature of nets is the possible synergistic resource interaction between the options. For example, SES and EW can be done together on lands growing biomass, meaning their effects are additive. But more data is needed to quantify these synergies. We will now move on to the discussion of process integration tools for mathematical programming. Process integration is now considered a powerful tool for planning low-carbon systems for sustainability. Tan and Fu in 2018 recognized the use of process integration tools for optimizing carbon management networks, or networks that deal with the flow of carbon. An example is shown on the figure on the right, where process integration tools were used to optimize a biochar supply chain network for negative emissions. And we can also take advantage of these tools in planning the wide-scale deployment of portfolios of nets. A useful tool is fuzzy set theory, which allows the partial membership of objects and was proposed in 1965. Bellman and Zade first used it for fuzzy decision-making, which seeks the intersection of the fuzzy goals with the fuzzy constraints. Years later, Zimmerman developed a generic fuzzy mathematical program formulation, which is the basis for the model used in this work. There are four types of fuzzy membership functions, namely maximum, minimum, trapezoidal, and triangular, depending on the goal. For example, the maximum fuzzy membership function is used for goals where higher values are more desirable, such as in economic performance. The minimum fuzzy membership function is used for goals where lower values are more desirable, such as in environmental impact. For a goal whose values must fall within a certain target range, like for example in production level, which must neither be too high nor too low, a trapezoidal fuzzy membership function may be used. A special case of the trapezoidal fuzzy membership function is the triangular fuzzy membership function. The degree of membership of each fuzzy goal or constraint linearly increases from 0 to 1, where 0 represents the least degree of satisfaction and 1 indicates full satisfaction. This slide compares the generic mathematical program with a generic symmetric fuzzy mathematical program. For the generic mathematical program, we have an objective function, inequality, and equality constraints. But for the fuzzy mathematical program, our objective function is to maximize lambda, or maximize the aggregate degree of membership. Because fuzzy optimization integrates multiple objectives into a single variable, which is lambda, or the fuzzy degree of membership. Fuzzy mathematical programming has been applied to nets, such as in the optimization of biochar networks for negative emissions, and the optimization of a combined biochar and enhanced weathering network, also for negative emissions. But so far, no work has been found on using fuzzy linear programming model for planning negative emission technology portfolios under capacity constraints. Another feature of nets which requires modeling is the synergistic resource interactions between nets. As mentioned, synergies may exist between the net options, meaning when two nets are implemented together, they use less amount of resource. A paper by Weber and colleagues in 1990 showed how to model synergistic projects so that they consume less resources, in this case, financial resources when taken together. The amount which the projects use less depends on the decision maker. A modified version of this model was used in this study. Let's now move on to the problem statement and objective of this work, as well as the optimization model. Given a set of negative emission technologies and resources like land, water, energy, etc., environmental footprints, fuzzy constraints for the annual capacity of each net, fuzzy annual negative emission targets, and possible synergistic interactions between nets. The objective is to determine the net's portfolio which will maximize the overall degree of satisfaction. In the optimization model, the objective function is to maximize the overall fuzzy degree of satisfaction, lambda. The next line ensures that the total capacity of the net's portfolio achieves the negative emissions target. The resource constraint ensures that the impacts on each resource are within the selected limits. The synergistic resource interaction is also accounted for in this constraint, wherein alpha is the synergistic interaction factor, which when multiplied with the amount of resource used by the net will give the discount value. If there is no synergistic interaction, the value of alpha is 0. Alpha is activated when the value is non-zero. The value of alpha ranges from 0 to 1 and will be determined by the decision maker. At the moment, the current synergy interaction in the model is limited to a pair of nets per resource. The fuzzy negative emissions target indicates that it's more desirable to maximize the negative emissions target, meaning a more stringent target. The fuzzy nets capacity indicates that it's more desirable to minimize the potential capacity of the nets for a more conservative approach on the capacities of these nets. Six terrestrial nets were considered, namely BECS, AR, SES, Biochar, DAC, and EW. The environmental footprints were based on the work of Smith and colleagues in 2016, and the potential capacities were based from the review paper of Fuss and colleagues in 2018, as shown in the earlier slides. The target negative emissions is based on the removal rates of 2.18 to 6.44 gigaton carbon equivalent per year from Rueda and colleagues in 2021. The resource constraints were based on the planetary boundaries reported by Rockstrom and colleagues in 2009. For case study 1, no synergistic interactions between nets were assumed. Solving the model results in an optimal nets portfolio as shown. Only the nets BECS, DACS, and EW were selected. AR and SES and Biochar were not included in the portfolio. Among the nets, EW has the highest negative emissions allocation, and the total capacity of this portfolio is 5.29 gigatons carbon equivalent per year. The land use and energy input limits were both maximized, and the fuzzy degree of satisfaction is 0.73. For case study 2, a special case of synergistic interaction between BECS and EW for land use was assumed, which is additivity. Based on case study 1, which is the baseline, we have an idea that EW will take the biggest allocation of land. Hence, we can set alpha so that BECS will not take from the land maximum limit of 436 million hectares. And this can be done by setting alpha for BECS equal to 1. Like in case study 1, only BECS, DACS, and EW were selected in the portfolio. Among the nets, EW has the highest negative emissions allocation. The total capacity of this portfolio is 5.55 gigatons carbon equivalent per year, which is 0.26 gigatons higher than case study 1. The land use and nitrogen limits were maximized. However, the sum 436 million hectares here is only for EW and DACS because we have set a synergistic resource interaction between BECS and EW. So BECS can be executed on the same land as EW so that it does not consume from the resource limit of 436 million hectares. The resulting lambda value is 0.79. For the two case studies, fuzzy constraints have been integrated to account for the net's capacity and negative emissions target. Resource constraints have been accounted in the model. Synergistic resource interactions have been integrated as well. Moving on to the concluding statements. A fuzzy linear programming model with synergistic resource interactions has been developed for optimal planning of nets portfolios. The model has been demonstrated with illustrative case studies. Current and future research will focus on including multiple synergistic nets interactions per resource, incorporating permanence and sink saturation of nets in the model, incorporating temporal and economic aspects, using alternative model formulations like robust and game theoretic, and using hybrid methods like p-graph and artificial intelligence. We have now reached the end of the presentation. We would like to acknowledge the Department of Science and Technology, Philippines, and the Engineering Research and Development for Technology Scholarship. Comments and questions are welcome, or you may also email me at this email address. Thank you very much.